Hello everyone, my name is Yingjie Zhang from Beijing Institute of Mathematical Science. Today I will present our work titled Linear Cumulacycles of Block Cipher LELBC. This is a joint work with Dr. Liu Gang. In this talk, I will present a semantic linear cumulacycles of the lightweight block cipher LELBC, including the search for optimal linear trails and the estimation of the linear Hall potential using MILP-based framework. Here is the outline of this talk. First, I will briefly introduce the motivation and the contributions of this work. Then I will give a short overview of LELBC cipher. After that, I will review some backgrounds on linear cumulacycles. Next, I will introduce our MILP-based automatic search framework. Then I will present our experimental results, including optimal trails and the 9-round linear Hall. Finally, I will conclude and discuss some future work. Lightweight block ciphers are widely used in resource-constrained environments, especially in IoT devices. LELBC is a lightweight block cipher designed for applications such as smart agricultural systems. Several cumulacycles results on LELBC have already been reported in the literature, but most focus on differential and differential linear cumulacycles. A semantic linear cryptanalysis evaluation using modern automatic tools has not yet been fully explored. Therefore, the goal of this work is to evaluate the linear security of reduced round LELBC at the distinguisher level using MILP automatic search method. For our contribution, first, we develop a unified MILP-based framework to automatically search for optimal linear trails in reduced round LELBC. Then, under the single case setting, we identify optimal linear trails up to 9 rounds. And third, by fixing the input and output masks, we construct the 9-round linear Hall. Finally, we estimate the ELP of this 9-round Hall. LELBC is a 64-bit block cipher with a 128-bit key and 16 rounds. The cipher follows a PSP structure, that is permutation, substitution, permutation. Each round operates on two intertwined 32-bit branches, and after the final round of the two branches are swapped, this structure allows efficient implementation in lightweight environment. Each round contains several basic operations, including add-round key, which XOR the state with round keywords, a 32-bit rotation, a cross-branch XOR, and a sublayer consisting of 16 parallel 4-bit SBox. In linear cumulacycles, the SBox layer is the main source of correlation. A linear approximation relates plain text, ciphertext, and key bits through a linear expression. The correlation measures the bias of this approximation. For a multi-round cipher, the correlation over a linear trail can be computed using the Pioneer lemma. However, many trails may share the same input and output max. Their combined contribution forms a linear Hall. Emulating all possible trails is infeasible in practice. Instead, we approximate the linear Hall potential using a subset of a dominant trio. This leads to the concept of ELP. We search optimal trios, fix the input and output masks, and then evaluate many trios and compute ELP. We formulate the search problem as an MILP optimization. The objective function minimizes the negative log of the correlation bound. Binary variables encode S-box correlation magnitudes. Constraints model the propagation of linear max through the cipher. The modeling components including XOR operation and rotation to branch and the S-box layer. XOR operations impose equality relations between masks, and the rotation operation corresponding to bit permutation, and the two-branch operation can be expressed using linear inequalities. For the S-box layer, we apply convex Hall inequalities that characterize feasible max transitions. This is the workflow. First, we construct the MILP model from the cipher specification. Then we solve it using MILP to obtain the optimal linear trio. Next, we fix the input and output and enumerate additional trios by adding no-good cuts. Finally, we compute the ELP. For reduced round up to 9, the optimal linear trios are better than or comparable to the best known differential trios at the distinguisher level. The best 9-round linear trio has correlation magnitude C equals to 2 minus 13. This trio serves as the starting point for constructing the linear Hall. After fixing the masks, we evaluate trios with correlation weight up to a given bound. In total, we found 156 trios contributing to the Hall. And then we compute the ELP by summing up the squared correlation of all trios. This corresponding to a distinguisher data complexity of about 2 to 57.42 non-plain text. Comparison with previous works, existing analysis mainly provide differential and differential linear distinguishers, and our work reach comparable strength at 9 round and complement previous results. To conclude, we propose an MILP-based framework for semantic linear analysis of LELBC, and we obtained optimal linear trios up to 9 rounds and estimated the 9-round linear Hall potential. Future work includes extending the analysis to key recovery attacks and exploring more rounds. That's all. Thank you for your attention. I would be happy to answer any questions.